Hello everyone and welcome to this presentation. My name is Adamos Christou and I'm a researcher at the University of Glasgow. I'm a member of the Bendable Electronics and Sensing Technologies group, and today I will present to you our work on selective printing of electronic layers for multi-layer devices using tailored surface morphology. I will begin this presentation by talking about printing of one-dimensional nanostructures for large area electronics. I will then present studies on the use of tailored surface morphology to achieve selective printing, including uneven surfaces with varying feature height and surface planarization. Lastly, I will discuss the merits of these techniques for multi-layer device fabrication before moving on to conclusions. One of the areas that we focus on in our group is the development of technologies for fabricating high-performance large-area electronics. One-dimensional nanostructures, like nanowires and nanoribbons, are great candidates for such devices and can find applications in areas like robotics, human-machine interface, prosthesis, and nanocomputing. An important challenge for realizing such devices has to do with the transfer of these nanostructures on target substrates in a precise manner and at controlled locations. Contact printing is a simple process which allows us to print highly aligned nanowire layers on rigid and flexible substrates. It can also be easily scaled up for large area electronics manufacturing. To do this process, we begin with a donor substrate with grown vertically oriented nanowires. We then press the donor against the receiver substrate and slide it while maintaining the applied pressure. As a result, the nanowires break from the donor substrate and transfer onto the receiver. And because of the shear forces between the substrates, the nanowires align along the direction of sliding. To carry out the process, we use a custom-built system that allows us to precisely control all the process parameters. For the purposes of fabricating devices, it is important to control the location where the nanowires arrays are printed. Different approaches have been reported to achieve localized contact printing. We have previously demonstrated a technique for selective printing where we used lithographically patterned resist layers to print nanowires at predefined locations. Another interesting approach is surface-controlled contact printing, where researchers have used miniature surface features to control local friction interactions between donor and receiver. This approach focused more on low-density nanowire assemblies at the selected locations. As we are targeting larger electronics, we are interested in high-density nanowire layers because this can benefit device-to-device uniformity and also device yield. In the studies that I will show next, we have explored surface morphology on the receiver substrate by introducing 3D features to selectively print nanowire layers. To create the 3D features, we deposit a pattern gold layer on silicon wafer. Because we wanted to explore the influence of the feature height, we tried different thicknesses of gold layers. And we also deposited a layer of silicon nitride in order to have a consistent material across the entire sample. The nanowires that we used for these experiments had a diameter of 100 nanometers. And here are the results we got when using features with smaller height of 20 nanometers. As you can see, the nanowires are printed uniformly across the sample, and the 3D features do not influence the printing in any way. Now, when trying taller features, this changed. These results were obtained with 3D features of 200 nanometers. And as you can see, the nanowires printed on top of the 3D features, or the peaks, have been reduced significantly. You also notice that the density in the areas between the features varied based on the area's width, with narrower valleys having higher density. From these results, we see that we can use 3D features on the receiver to selectively print nanowires using the contact printing process. In the next study, we explored what happens when we want to get uniform printing, but we are presented with the receiver substrates having uneven surfaces. For this, we prepare a different type of receivers where we spun a layer of polymite over the 200 nanometer pattern gold layers, and then we deposited the silicon nitride. This can be seen from AFM analysis. The addition of the PI layer creates a smoothed out slope at the edge of the features when compared to our previous receivers. Interestingly, by adding the polymite layer, we observed that the nanowires were printed uniformly over the sample with the 200 nanometer tall features. This shows that planarization of a receiver surface using polymite can be used to negate the effects of the uneven surfaces during contact printing. Now, let's talk about why these results can be of use. First, we can use 3D features to control the location where the nanowire layers are printed. Creating these features adds a level of complexity in the contact printing process. However, we could actually use existing features on a receiver, for example, channel contacts of a device, to selectively print nanowires across the channel. If we now consider multi-layer printed devices, there is a chance that uniform printing is needed over an uneven surface. And in this case, the height of the features can be tuned accordingly. Alternatively, we can use planarization of the uneven surface to allow uniform printing over tall features. To conclude this presentation, I have discussed the printing of one-dimensional structures for fabricating large area electronics. I then presented studies on the use of tailored surface morphology for selective printing of nanowire layers, where we examined the influence of the feature height and surface planarization. And finally, I discussed the merits of the presented techniques for the fabrication of printed multi-layer devices. At this point, I would like to thank the Engineering and Physical Sciences Research Council for supporting this project, as well as the members of the Bendable Electronics Assistive Technologies Group for their help and their support. Thank you very much for attending this presentation, and please feel free to visit our group's social channels for more information on this work as well as other projects.